So continuing on with our discussion on atomic and nuclear physics, let's take a look in this video. Let's take a look at the concepts of atomic line spectra, energy levels, and the hydrogen spectrum. First, let's talk about the atomic line spectra and energy levels. When you have a beam of light, we can separate the beam of light into various wavelengths using a prism or diffraction grating. We can separate the wavelengths into what is referred to as a spectrum, wherein we see the colors which consists which is consisted which the light is consisted of. If the source if the light source is a hot solid or liquid, the spectrum is continuous, meaning all light of all wavelengths are present. So all colors are present. You'll see a gradual transition from red to violet. But if the source is a gas carrying an electric discharge, only a few colors appear, and we see sharp parallel lines being formed in the spectrum. It's not a gradual transition. It's not a gradient from red to violet, colors of the rainbow. You will see basically bands of colors, lines of colors, parallel lines. A spectrum of this sort is called a line spectrum. And the emission of atoms, you see a line spectrum. Atomic and molecular emission and absorption spectra have been known for over a century to be discrete or quantized, meaning you have an atomic line spectra when you look at the absorption spectra or the emission spectra of atoms. That they are only able to absorb and emit certain wavelengths of light or certain frequencies of light. Bohr hypothesized that each atom must be able to exist only within certain values of internal energy. Each atom has a set of possible energy levels and cannot have an energy level intermediate between two levels, meaning the atom in terms of energy may only transition from one energy level to another, emitting certain emitting only certain values of energy, which means emitting only certain frequencies of light. An atom can make transition from one energy level to another by emitting a photon with energy equal to the energy difference between the initial and final levels. Meaning, if the atom transitions from one energy level to another, so you have from one energy level to a lower energy level, so you have initial energy level, final energy level of the atom, the difference, E initial minus E final, the difference will be the energy of the emitted photon. So E initial minus E final is equal to H F is equal to Hc over lambda. Similarly, the reverse has also been shown to be true. An atom can jump from one energy level to a higher energy level by absorbing a photon. EF minus E initial is equal to the absorbed photon energy. HF is equal to EF minus EI. So the difference between this equation and the previous equation is that here, the in the first equation, the atom goes from higher energy to a lower energy level. So E initial is greater than E final. Whereas in the second equation, the atom goes from lower energy level to higher energy level. So EI is less than EF. The lowest energy level of an atom is called the ground state energy level, or simply ground level. And all higher energy levels are excited level. Let's focus on the hydrogen. The hydrogen atom, the emission spectrum of the hydrogen atom has been shown to be a line spectra, has been intensively studied. Balmer found a formula that gives the wavelengths of this line. 1 over lambda is equal to capital R times 1 over 2 squared minus 1 over n squared, where n is equal to 3, 4, 5, 6, 7, and so on. So note, lambda here is the wavelength of the emitted photon when the atom goes from higher energy level to a lower energy level. This series is referred to as the Balmer series. Capital R is the Rydberg constant or Rydberg constant, equal to 1.097 times 10 to the 7th power per meter. Now, turns out this is just one series. Other spectral series for the hydrogen have also been found. You have the Lyman series or the Lyman series. 1 over lambda is equal to R times 1 over 1 squared minus 1 over n squared is equal to n is equal to, so about that, 1 over lambda is equal to R times 1 over 1 squared minus 1 over n squared, where n is equal to 2, 3, 4, 5, 6, and so on. There's the Paschen series. 1 over lambda is equal to R times 1 over 3 squared minus 1 over n squared. This time n is from 4 onwards. 4, 5, 6, 7, 8, 9, 10, and so on. Bracket series. 1 over lambda is equal to R times 1 over 4 squared minus 1 over n squared. N is equal to 5, 6, 7, 8, 9, 10, and so on. Bracket series. Lastly, we have the fund series or P-fund series or fund. 1 over lambda is equal to R times 1 over 5 squared minus 1 over n squared. N here is equal to 6, 7, 8, 9, 10, and so on. So you have 1, 2, 3, 4, 5 series for the spectral lines of the hydrogen atom. This series suggests that the hydrogen atom has a series of energy levels given by E sub n is equal to minus HCr over n squared. N is equal to 1, 2, 3, 4, 5, and so on. So you have E1 E2, E3, E4, and so on. And depending on the transition from one energy level to another, you have the different you have the different emission spectra series. This equation tells us that the energy of the hydrogen, the energy of the electron in the hydrogen atom is quantized, which is consistent with what we have covered when we looked at Schrodinger's equation being applied to the hydrogen atom, resulting in the principal quantum number n and the energy being quantized. So consistent, the emission spectra of the hydrogen atom is consistent with what we covered with Schrodinger's equation. So that's it for now. In the next video, we'll take a look at the concept of the laser. So thank you for watching.